Last time, we studied the equation y equals w transpose x. No matter how many independent variables we have, we can still express everything with this simple form. And our goal was to find the model parameters, the w vector. How did we find it? Through the mean squared error, or MSE. But when I look at the vector formula, that sigma symbol kind of bothers me. Wouldn't it look much cleaner if we expressed it using matrix and vector multiplication instead?
Like, comment, subscribe, and turn on notifications.
The MSE is our loss function, and that loss function can actually be written in matrix notation as well. Much simpler, right? So now let's see why these two forms are actually the same. First, let's simplify this table a bit. We'll remove the unnecessary parts, and to include the intercept term, we'll add a new column of 1s to the X matrix. Check the table on the left side of the screen. Now, on the right, we'll represent the independent variables as the X matrix, and the prices, or the target values, as the Y vector. Remember, vectors are written in lowercase and matrices in uppercase. All right, let's start from the equation on the left. We have 5 rows of data. For each row, we take the inner product of the features with the W vector, subtract the actual Y value, square the result, and sum them all up. That gives us SSE, the sum of squared errors. And dividing by 5, we get the MSE. Now let's look at the matrix notation on the right. We multiply the X matrix by the W vector. Matrix vector multiplication works like this arrow here, row by row. If we continue that process, the result of XW looks like this. Now we subtract the Y vector. So the expression becomes XW minus Y. Each element of that vector corresponds exactly to the term W transpose X minus Y on the left-hand side. Since the formula is getting a bit long, let's label each row as A, B, C, D, and E. Now let's rewrite the right-hand side in that form. The squared 2 norm of a vector is the same as its inner product with itself. We still have 5 data rows, so we multiply by 1 over 5 and take the inner product. And there we have it. It's exactly the same equation as the vector form on the left. Alright, so this is how the MSE can be written in matrix form. We can take the partial derivative of L of W with respect to the weight vector W and find the W vector that minimizes L of W. Remember, last time we looked at a 3D graph of L of W and we saw that it was a bowl-shaped surface, convex with respect to both components of W. Even if W has more than 3 components, L of W remains convex in every direction. We can actually extend what we learned last time and prove that mathematically. Now, since L of W is convex in all components of W, we can find the optimal W by taking the derivative of this matrix expression and setting the gradient to 0. Let's differentiate this expression in matrix form. The squared 2 norm, that is the squared length of a vector, can be written as the inner product of the vector with itself. When we move the transpose inside the parentheses, the multiplication order changes, like this. Now, let's expand this using the multiplication rule. These two terms are transposes of each other, so their values are the same because a scalar value doesn't change when transposed. You can actually check it yourself. Pause the video and try it. You'll see they're identical, and it'll help you remember this much longer. Once you get used to it, you'll quickly notice that this vector matrix vector structure always results in a scalar. Since the two terms are equal, let's unify them as Y transpose XW. That gives us a term that starts with minus 2. Now, if we differentiate this expression with respect to W and find where the derivative equals 0, we get our optimal W. Let's use the differentiation rules shown here. If you're curious how this table was derived, I'll make a separate video on that when I get a time. All right, let's go through the differentiation. For the first term, using the last rule from the table, we treat X transpose X as one matrix and get this result. When any matrix X is multiplied as X transpose X, the result is a symmetric matrix, and it's also positive semi-definite. Let's first see what symmetric means. If X is a 3 by 2 matrix, then X transpose X is a 2 by 3 times a 3 by 2 matrix. So the result is 2 by 2. And as you can see here, the blue parts are identical, so transposing it gives the same matrix. That's what we call a symmetric matrix. Now, positive semi-definite basically means that the coefficient of the squared term in a quadratic expression is positive. In other words, no matter which direction W moves, the surface of L of W curves upward. It's convex, just like we saw earlier. We'll revisit positive semi-definite matrices when we talk about eigenvalues in PCA, and again later during optimization in deep learning. If you already studied linear algebra, this might sound familiar. Let's continue the differentiation. Since X transpose X is symmetric, we can simplify the two matrices as identical. Now for the second term. According to the first rule, it becomes minus 2x transpose y. The last term doesn't contain w, so its derivative is 0 and it disappears. Now, this entire derivative should equal 0. We can remove the factor of n on both sides. Remember, whether we use MSE or SSE, the value of w we get is the same, since that 1 over n factor doesn't affect the result. And if we multiply both sides by 1/2, the factor of 2 also cancels out. Now we're almost there. Solving for w, we get w equals x transpose x inverse x transpose y. And that's how we get the direct solution, also called the normal equation for linear regression. All right, now let's take a closer look at this direct solution. Since it's a linear model, if the inverse of x transpose x exists, we can find the weight vector w directly, just using our input data matrix x and the target vector y. For example, if we have this data set, we can represent the independent variables, like the number of rooms, bathrooms, and so on, as the matrix x, and the house prices as the vector y. Then, by plugging them into the equation, we can directly calculate w. So basically, the direct solution is the result of setting the partial derivatives of L of w with respect to each component of w equal to 0, and solving that system of equations all at once. When there's only one feature, we can visualize L of w geometrically along with the intercept. But once the number of features increases, L of w becomes higher dimensional, beyond 3D, so we can't visualize it anymore. But the mathematical principle is still exactly the same. Now let's take a look at this with some code. Here we'll model this data set linearly and calculate the weight vector w. Our goal is to find the relationship between the independent variables, the number of rooms, bathrooms, and the year built, and the dependent variable, the house price. I'll keep the explanation simple since most of you are already familiar with Python code. First, we load the data set using pandas. Then we create a matrix from the independent variable columns and a target vector y from the price column. Now, here's the most important part, the equation for w. Can you see how this formula matches the code above? Let me show you how they correspond line by line. But if you've already tried using machine learning libraries like scikit-learn, you might notice that this approach looks a bit different from what you've seen before. Let's check TensorFlow, for example. The data loading part looks similar, right? But here, the matrix doesn't need a dummy column. It's just x, not x bar b, because the dense layer in TensorFlow automatically learns the bias term internally, so there's no need to add a dummy column manually. Sequential is basically a container that holds our neural network, and dense represents a fully connected layer. We set the input shape to 3 columns since we have 3 features, and the output to 1, which represents the predicted house price. We're using SGD, stochastic gradient descent, and the loss function here is MSE, mean squared error. The model is trained for 100 epochs, and verbose equals 0 just means it won't print the training progress. After this process, we obtain the weights and bias, which together make up the vector W. Alright, now let's move on and take a look at scikit-learn. Since the code is really simple, I'll skip the detailed explanation here. You can check the code yourself, but I have one question for you. When the fit method runs in TensorFlow or scikit-learn to find W, do you think it uses the direct solution internally? The answer is no, it doesn't. And the reason is that the normal equation is computationally expensive. Especially this part, the matrix inverse, has a time complexity of big O of D cubed. Here, D represents the number of features, which means the number of independent variables. In our house price example, D would be the number of columns like area, number of rooms, and so on. Let's see why that's the case. If the X matrix has a shape of n by D, then its transpose, X transpose, is D by n. When we multiply them, we get X transpose X, which becomes a D by D matrix. Now, let's take a look at why the inverse operation has a complexity of big O of D cubed. Here's the code for the inverse calculation implemented with Gaussian elimination. If you look at the highlighted section, you'll notice it has 2 nested for loops, so that's D squared operations already. And at the bottom, there's an additional vector operation of length D, making the total complexity big O of D cubed. So, instead of using this computationally heavy normal equation, what kind of algorithm do we use? We use iterative methods, and the most famous one is gradient descent. Gradient descent gradually moves toward the optimal W step by step. How does it know which way to move? As you might have guessed, it goes in the opposite direction of the gradient, because that's the direction of the steepest descent, the fastest way to decrease our loss. Mathematically, this process can be written like this. This update rule allows us to efficiently find W with a time complexity of roughly big O of D, which is far more efficient than the direct solution.